welcome back. Last time we covered tree traversal strategies in detail. We looked at pre-order traversal, in-order traversal, and post-order traversal, as well as breadth-first search. And the way that we did pre-order traversal was with a basic stack. The way that we did in-order traversal and post-order traversal is we looked at a recursive solution for those. We also observed, of course, that you could do those with stacks. You just need to keep track of where you are and where you came from in order to determine, should I be doing an in-order traversal, a post-order traversal, or a pre-order traversal. We also looked at a breadth-first search, which was a top-down, left-to-right kind of traversal strategy. Yep, we're good. That used a queue. So instead of putting things into a stack, we realized that if we use a slightly different data structure, we'll get completely different behavior. One thing I screwed up on last time was the iterator pattern here, and I wanted to revisit that first before we move on. So remember, the idea here is that I've got a binary tree, and I want to iterate over it using an enhanced for loop. And to do that, what you need to do is you need to make it implement the iterable interface so that there's this collection that you can iterate over the elements. If it's a list, of course, that's straightforward, right? You start at the first node, and then you hop over to the second node, the third node, etc. If it's an array-based list, then it's even more straightforward because you just need to keep track of an index variable. But over here, if we're going to do a pre-order traversal, right, where's my regular pre-order traversal? There we go. If we're going to do a pre-order traversal, we need to keep track of a lot more information. We need to keep track of a stack and then the current node that we're currently on. And the reason that I screwed up last time is that I thought that you could have a constructor in a anonymous class, but you can't. And so we're going to have to do this a little bit differently. Let me go ahead and start by letting it generate those two methods. Let's go ahead and go with return new iterator for elements of type T, and then we'll define it anonymously in line here. This is just like a comparator, right? That we're creating it here and we're defining it here because it has one use and one use only. We're not going to be creating instances of this. Like, we've got 5 different invoices, so I do need an invoice class because I'm going to create 5 different instances of it. Here it's just one thing, and it has one job: to iterate over the nodes in this tree. So the first thing I'm going to do is bring down, that's breadth first search. Let's go ahead and bring down this stack up here, right? And I'm going to make that, just like I did last time here, into a private variable. It doesn't really matter that it's private, by the way, because this is an interface, so nobody's going to have access to this anyway. But the key difference here of what I did last time is I'm going to keep track of the current variable. So private binary tree node current. And I'm going to initialize it to this tree's root. Now we'll come back to this here in a second because it's not going to compile. But the idea here is that I've got a pre-order traversal, and X is acting like my current node, right? If you want to think about it like a little guy that's standing on this current node, right? Where initially he's going to stand on the root, and then he's going to take a walk around this tree. He's going to go left, and then eventually when he comes back, he's going to go right. So he's walking around this tree, and the node that he's currently on, that's going to be my current variable. Up here, I just went ahead and popped it off the top of the stack and called it X. But now down here, I'm going to have to keep track of it, current. Now to get this to compile, we're going to have to resolve what this is. This is referring to this object right here because we're inside this object. So this does not have a root. That has a root, right? The binary tree itself. And because we're inside that class, it can resolve what the root is. So it's not a superclass, it's not inheritance here, it's encapsulation, right? We're doing what is almost essentially is called a closure, but that's more of a functional programming language kind of thing, right? So I've started by putting the little guy on this first root right here, okay? Now, to determine whether or not you have another variable or another value to give, right? All we need to do is say, is this guy standing on a current valid node, right? And so in other words, if current is not equal to null, then yes, then return true, right? Otherwise, if current is null, then the guy that we're walking around here on this tree has walked off the tree and we're done, okay? So I'm going to simplify that to return current, and this dot current is not equal to null. There we go. So do you have another value to give me? Yes, I do, because I'm standing on that value right now. Again, this little guy is walking around the tree, and initially he's on this route, and eventually when he comes all the way back, we're going to have to make sure that he steps off this tree once he's done exploring this entire tree. Okay. So now what we need to do is actually implement the next. Okay. So I'm going to go ahead and save off the value that's stored in the current node, right, is equal to current dot get element, and that's what I'm eventually going to return. Okay. So the thing that I'm standing on right now, the thing that the guy is standing on, this is the next node. I'm going to go ahead and take that variable out and give it back to you. But I need to make sure that I'm setting myself up for the next iteration, right? I'm going to go ahead and give this A to you, right? But then I need to take my walk. I need to go ahead and go over here. But be careful. What else do you need to do before you walk over there? You need to make sure that you are pushing this variable and this variable, right? Or that node and that node, excuse me. Right? Just like the stack up here. The idea here is that you're taking out the while loop, right? That the outside world is responsible for this while loop now. This enhanced for loop. It's responsible for asking, do you have another one? Okay, great, yes. Then go ahead and give it to me. Do you have another one? Yes, give it to me, right? And so it's taking care of that while construct right there for you, okay? And I'll go ahead and grab both of these and move down here. Right? And it's not X anymore, it is the current. Current.getChild and current. X is the actual element that we're returning there. So I push the right child, I push the left child. Let's see if this works. It's probably not going to work because there is an intentional bug, but let's see how it fails. There we go. So it's stuck in an infinite loop here, always at A. In other words, the guy never gets off of this variable right here. So let's go ahead and go back over here and realize what our mistake was. All right? If we walk through this, right, then you're always saying, yes, you do have another variable because I'm standing on A. Here you go. Okay, give me that variable. I grab that out of the node. I push the right child, I push the left child, and then I return the node. Did I ever make the guy change his node and go down to the next one? Nope. So what I need to do is I need to make sure that I'm walking down to the left node or to the next node. Now the next node could be the left node or he's returned and he needs to go down to the right node. In either case, it's going to be at the top of the stack. So this dot current is equal to this dot stack. Oops, what did I call my stack? S? Yep, there, dot S. Dot pop. There. Now let's see if it works. It's going to work a little bit better, but probably not fully. Let's find out why. You know what? Let me change this to the small tree. Small tree. There we go. And we've got A, B, D, E, C. We never get to the last one. If you remember what that tree looked like last time, let me go ahead and bring it in really quick. Oops. The small binary search tree. There we go. So the order of pre-order traversal was going to be A, B, D, E, C, F. Right? So we've got it correct up to except for F. Now remember what I said? We're going to have to make sure that this guy steps off. Right? How are we going to step him off of the tree? Right? Goes down here, he explores everything. Goes down here, he explores everything. He comes back, and eventually, what do you need to set this to? Right now, it's complaining because you tried to pop off an empty stack. So what's one thing that we could try here? Ask, is there an element to pop off? If this dot s dot is empty. If it's not empty, then what should we do? Then go ahead and pop it off. Right? Otherwise, don't pop it off because that would throw an exception, and we see that right here. How do I set a flag variable to indicate that it's no longer an element there for you to stand on? Now he's fallen off the tree. Right? Let's see if that worked. A, B, C, D, E, C, A, B, D, E, C, F. Right? And if we change this back to the large tree, just to make sure that it runs and that it stops, right? There we go. And if you want to, you can go back to the last lecture and see if that actually matches. You can reformat this so that it's an in-order traversal. You could reformat, and I think I do that in the pre-prepared videos. You could do this so that it matches a BFS instead, right? Breadth first search, where you go top to bottom, left to right on each level. All you would need to do is change your stack to a queue, and then change everything to offer and switch them around. Okay, great. So that brings us up to date here. So there's really not much we can do with these trees. Right? Let me go back over here and ask you, what's it going to take to find a variable with just this structure right here? What if I'm searching for the thing stored at I? Right? Well, if I did a pre-order traversal, what would I end up doing? I'd come down over here, explore this entire subtree over here, right? And then come back over here, explore this. Oh, and then I finally get it over here. What if I were searching for J? I would end up exploring more than half of the tree just to come over here to this, this variable over here. What if I did it for BFS instead? Right? I would have the same problem. And ultimately, I'm going to have to look at everything in order to find what I'm looking for. Right? So my first observation here, we'll come back here with a title. My first observation is that pre-order, in-order, post-order, and even BFS are all linear algorithms. Right? They're all order 1, or n, excuse me, 1. Why is that? Well, all they're doing is going over the entire tree. How many nodes are in the tree? N, right? Each node is processed exactly once and visited at most 3 times. Why 3 times? So here's the node. You come in the first time, you go down to the left, and then you come back to it, right? And then you go down to the right, and you come back to it. So ultimately, you could be visiting it at most 3 times, but that's still going to be order n, right? So whether or not you consider traversal or processing or whatever as your elementary operation, it's still going to be a linear time algorithm because you're doing this for n, I'll note that here, n nodes in the tree. Right? So we need more structure because this is really no better than a linked list. Right? It's just a little bit more complicated, right? So extra steps. It's a linked list with extra steps at this point. So what we're going to do is we're going to introduce more structure, right? And that's going to be binary search trees. Okay. Binary search trees have the following properties. So property definition. Right? Each node contains data and a key. For our purposes, the key will be the data. Right? We're going to keep it simple. You could, of course, change your tree node so that it holds data and then a key, and then the key is what you're looking at as far as ordering goes. Instead of A, B, C, D, E, F, G, H, I, J, K, you are storing A, B, C, D, E, F, I, J, K, but then also an invoice with it or something. Okay? So, the tree will have the following binary search tree structure or property. For each node, U, right, the key, every key in U's left tree will have a key value less than u. Right? And every node in u's right tree will have a key value greater than u. Right? So let's go ahead and picture this first of all. Okay. So if I've got a node u here, it has some sort of a key. I'll just call it k. Okay. Now over here on the left subtree, there could be a lot of different variables, a lot of different nodes, a lot of different values, but they're all guaranteed to be less than k. Over here with our right subtree, we're going to have values that are greater than k. Now, why does that help us immediately? Think binary search. Right? You look at the one in the middle, right? And if that's the guy that you're looking for, great, you're done. But if that's not the guy that you're looking for, where do you go? If it's less, then you go over here to the left subtree. If it's greater, then you go over here to the right subtree. Let's take a look at an example. Binary search tree. So this is the same basic structure that I had before, but I've replaced all those A, B, C, D, E, F, Gs with actual numbers. Now let's verify that this is indeed a binary search tree. Up here at the root, we have 50. Look at everything in the left subtree. Is it less than 50? Yep. Look at everything in the right subtree. Is it greater than 50? Yes. That is an inductive property that holds for every node. For example, let's go ahead and look down here with 20. Everything in its left subtree is less than 20. Everything in its right subtree is greater than 20. That has to hold for every node, not just the root node, but for every node. Okay? So what about ties? Do we allow duplicates or not? Well, if you don't want to allow duplicates, then you program it that way. If you do want to allow duplicates, you need to say what?
Do you have like 3 per node?
No. Instead, you just break ties one way or the other, but be consistent, right? Ties will go to the left. All right, they all go to the left. Oh no, I want ties to go to the right. All right, they all go to the right, because you can't guess. Oh well, the 50. This is not the 50 I'm looking for. The 50 I'm looking for is a little bit different. Do I go left or do I go right? I have no idea, because if you don't have any consistency, then you're guessing. Right?
I don't know. Hard to say. The entire tree is made up of 50s.
You can support non-unique values, right? You can but most data structures will support unique keys. Right? They have to be unique somehow.
At least certain that if it was just the same variable all the time, it would just be a linked list, basically.
Yeah, and you might not need to store it, but you can have duplicates. You could have, say, invoices. You could have 50 invoices that are all $100, right? And that's valid data, right? So what you do is you break ties some other way, right? Some unique identifier, like your database key or the code or something like that, okay? So you usually have some tiebreaker where you don't allow duplicates, right? And if you do allow duplicates, then it can't tell the difference between these two things. So they might as well be the same. All right, so how does this help us? Right? My first observation on this is that to find an element, you simply need to traverse one way or the other until you find it. Right? Similar to binary search. And now you know why we call them binary search trees, right? Because it's kind of like binary search. It's a binary tree. They're at most 2 children. And it basically gives us the best of both worlds. It gives us the potential for very fast operations, because it's going to be proportional to the depth, but also it doesn't lock us into having an array and having random access. And all the problems that we have with an array or an array-based list, where if you want to insert something at the beginning, you have to shift everything down. That's going to be an order n operation. let's look at this and try to derive, and that's not what I want. Let's try to derive an algorithm for search. Right? I want to find, say, 50. All right. There's my first example. We're gonna try several examples here until we find a pattern that we can then implement. All right. So where do I start? Usually, just like everything, I start at the root. And guess what? You find it at the root and you're done. Right? So my first observation here is you quit, you stop, you terminate once found. There we go. So that's going to be one of our stopping conditions. Let's go ahead and find another value. Let's go ahead and find, I don't know, 49. Okay. So what do? I come in here to the root. I see that the thing that I'm looking for is not equal to 50. 40, I'm looking for 49, and so I traverse left. Okay. I then compare my key value here to 40, and I see that the thing that I'm looking for is not equal to that, but the thing that I'm looking for is greater than that, so I traverse right. I see that the thing that I'm looking for is greater than 45, and so I traverse right. And at that point, I'm done. Right? How many comparisons did I have to make to do that, by the way? 4, right? So this was only one comparison. This was 4 comparisons. Right? What about finding 12? Let's look at that. Yep, I'll go ahead and speed run that one. 1, 2, 3, 4, 5, 6. Right? At most 6 comparisons. You do have to compare it to the last one to see, is this the thing I'm looking for? Right? I counted right. Yep, there we go. All right. What about 13? Are you going to find it? No. No. You do have to make sure that you are handling unsuccessful searches. So what would you end up doing? 1, 2, 3, 4, 5, 6, 7. Actually 6. And then finding out that it's null, right? So unsuccessful search, not found. Ultimately, I made 6 comparisons. So one of our stopping conditions is once you find it, you're done. Stop. Right? If you've not found it, then you've fallen off the edge of the tree. Right? If it had existed, where would it be? Right here, hanging off of 12. And so since this is null, then you say not found. And it took me 6 comparisons.
Shouldn't 13 have gone before 12?
What do you mean?
10, 15, 13, and then 12.
10, 15, 12, 13. Nope. Where do you think that it should be?
So, the 13 would also be less.
You could reconfigure this completely if you had that luxury. No. You could reconfigure this completely, and then if you want to hang 12 and 13 off of this, you could say, oh, 13, then where would 12 be? As a left child. But that's not what this tree is. The topology of this tree is given, right? We'll talk about how to get stuff into this tree here in a moment, okay? So my first observation is what? All searches will be proportional to the depth. All searches will be order D, where D is the depth of the tree, right? Some of them are going to get lucky, right? You're going to find them shallow in the tree. Other things are going to be less lucky and you'll find them lower in the tree. Other things are going to be completely unlucky and you don't even find it, and it's going to be proportional to the depth, right? Observe. If the depth is efficient, right, then or D is equal to order log n, then searching is efficient. Or at least it's as efficient as a binary search. Right? do we have that guarantee? Let me go ahead and give you a tree here. Nope, not necessarily exactly. Why? 10, 20, 30, dot, 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 all the way up to 100. So 10 nodes here, what's the depth? Careful, it's off by 1, 9. In other words, in this case, the depth is going to be order n. That's a binary search tree. Right? It's just a degenerate one that has skewed all the way to the right. Give me another name for this. Exactly. Right? What is it? A linked list. Right? All you have to do is depict it as such. So you can have degenerate trees where you don't have that property. Right? So this is not all. However, this is not a guarantee. Right? So we'll talk about making sure that there is a guarantee for this later on. We won't get too much into that depth. They're called balanced binary search trees. Before we get there, though, we need to look at these basic operations. Let's go ahead and start with an actual implementation over here. Question? No? Okay. All right, well, I've already got a binary tree. Maybe I could create a new class here, a binary search tree, T, right, that extends my binary tree, T. In other words, a binary search tree is a tree, right, with just more specific behavior. Okay. There we go. I'll go ahead and leave it like that. Let's take a look at these this interface over here. An in-order traversal, post-order traversal, pre-order traversal, breadth first search. Do all of those make sense necessarily for a binary search tree? I don't think so. Why are we inheriting that behavior when it doesn't make sense and we're not going to use it? Right? Maybe there's a reason for this, I don't know. But in any case, let me go ahead and change this so that I'm not doing that yet. We'll consider that later on, right? We'll come back to that. Right? So I'm going to go ahead and copy and paste this right here, this root. I am going to reuse my binary tree node because a binary tree, it's the same, right? It holds an element, et cetera, right? So this dot root is equal to root. All right. Help me out. Let's go ahead and implement this find method. Right? And to do that, I'm going to go ahead and call this public Boolean contains. Okay? And does it contain an element of type T? Is it in the tree? Because if you already have it, then you find it in the tree. Great, you have a duplicate of that value. Okay, and we're going to return true or false here on whether or not it contains it. So in other words, we need to do search the tree to find an element that matches X. Right? So 1. Start at the root. Right? 2, while you are on a current vertex, or current node, let's say, right? A, compare the current vertex or node to X. And one of 3 things will happen. A, it matches. Stop, return true. B, X is less than the current node. Traverse which direction? C, X is greater than the current, or here I'll rewrite it as current is greater than X, or is less than X. Traverse which direction? Right? So the current node, X is less than that. Do I go left or right? No? So X, the thing I'm searching for is less than the current node, so I traverse left. Right? Otherwise, I would traverse right. Right? Now, what's my third condition here, my stopping condition? Until you find what you're looking for, in which case you would return true right here, or until you reach the end of the tree, in which case I return false, because you didn't find what you were looking for. Okay? All right, so let's go ahead and translate this now line by line. Start at the root. I need a binary tree node to represent the current node. Current is equal to root, or this dot root. There we go. While you're on the current node, or compare it, right? So let's go ahead and write a bunch of if statements here. Right? If it matches, stop and return true. So what I mean by matching here is that the current dot get element, there we go, is equal to equals, I'll write it like this here, equals x. Right? If that's the case, I return true. Yes, you have the value x in this class here. Right? All right, can I use equals equals? Does that work in Java? Does that work in C? Does that work in any statically typed language? What type is X again? Type T, right? Does it work with strings? No. Does it work with integers? Yeah, it would. Does it work with doubles? Yeah, it would, probably, right? But does it work with strings? No. Would it work with invoices? Would it work with people? Nope. So what do I need here? How do I tell this object is equal to that object? Dot equals. No, that's one way of doing it, right? We'll see if that's sufficient. Okay. Okay, else if the thing that I'm looking for, x, is less than the current element. So there's my current element, and there's x. If it's less than that, then I will traverse. Here, let me move this up here, and traverse left. Now, what does that mean? That simply means that current is going to be updated to current dot get left child. That's not compiling. We'll come back to it. Else if the current dot get element is less than x, then we need to traverse right. There we go. So current is equal to current dot get right child. There we go. Until you reach the end of the tree. So all of this stuff should have been in a while loop, right? So let me go ahead and put my while loop up here. While some condition, and again, it's not compiling because we need a lot more stuff here. There we go. Until you reach the end of the tree and return false. Right. That will compile. What's my condition here? Until you reach the end of the tree. I'm sitting on a current vertex. I'm sitting on a current node, right? Yes, continue. Yes, continue. Yes, continue. Yes, continue. Yes, continue. You've fallen off. What is the right child here as far as Java is concerned? Null. Right? And so, while the current node that you're standing on is not equal to null, then keep looking for it. If you ever find the thing that you're looking for, great, go ahead and return. Otherwise, once you've broken out of this loop, return false. One of those three things compiles now. So what's the problem here? Less than. Does that work for integers? Yeah. Does that work for doubles? Yeah. Does that work for strings in Java? No, it doesn't work for strings in C either. What are you doing? You're asking in C, is this string, is this string's memory address, is it less than this string's memory address over here, which is nonsense because it might get loaded up completely non-deterministically. Right? Okay. I don't know how do we compare these things?
strcmp.
strcmp. That'll work if it's strings. Do I know that they're strings?
No.
What are they? T's.
To make it give us a comparator?
Ah, there we go. So if you want to make this generic, then you need a way of saying sort, collections.sort. I'm going to go ahead and give you a list of elements of type T. What else do I need to give you in order for you to say this thing comes before this thing? A comparator. Right? 4 elements of type T. And I'll just call this CMP. How are we going to get this into our class? A new comparator for elements of type string. I can't do that. T. Right. Well, that. Nope.
Because that type should have comparator credit in it, or that class.
I can add like a compare to method here, but I've got T and T. How do I compare them? Nope. That's not on me. That's on you outside the class. If I want a new binary search tree now, for strings, what do I need to give it? Binary search tree for strings. I need to give it that comparator. Right? And foo and bar. We'll come back to this. There we go. I'm going to have to give it to you. Right? And so let me go ahead and give it as part of the instantiation here. You'll give me the root, and also you'll give me the comparator for it. Right? And at this point, I'm rethinking whether or not we should even have the root here, because I'm going to go ahead and start with an empty tree. Right? There we go. You give me the comparator. Eventually, I'm going to allow you to put stuff in and take stuff out and search for stuff, et cetera, et cetera. So you just need to give me a comparator to tell me, when I've got 2 nodes, how do I know that they're equal? How do I know that I need to traverse left? How do I know that I need to traverse right? Right? Now let's come down here and recast this in terms of the comparator. I don't know how to compare these 2 things, but if I ask this.cmp to compare x and this element over here, right, it'll do one of 3 things. It'll return something negative, positive, or 0, depending on the relative ordering of those 2 things. If it returns something negative, that means that x comes before the current element. If it returns something positive, actually I'll rewrite this entirely. This.cmp.compare cmp.compare, come on, cmp.compare to current.getElement and x, and if that is less than 0, I'll go ahead and go right. So note here that but they're both less than 0. Why? Because I swapped x and the current element here. That's how I personally like to think about it. If you want to, you can go ahead and make this so that that this would be x and then the current, and then that would be greater than 0. Right? I'm just swapping them here. In fact, it really doesn't matter. Do you need this? It's either equal, in other words 0, and I should probably properly do that, right? It's going to be equal if it returns 0. Now, strictly speaking, do I need this third if statement right here? It's either 0, greater than, or less than, right? So I could go ahead and get rid of this entirely. I'll leave it in here for when I post the notes, okay? I have no idea if this works or not, because I've not built a binary tree yet. We can do that really quick, though, over here in the demo, maybe. All right. So first of all, I need a comparator for strings. Comparator t cmp strings is equal to new comparator for elements of strings. Sorry, I need to actually say that it's for strings. There we go. Bring this in, import this, add unimplemented method. There's my string 1 and string 2, s and t. And I'll simply just say s.compare2, because they're already comparable, right? There's something built in for me to do that already, and I'll just return that. And I will give you this string comparator. There we go. So I could manually build this tree. What I would have to do is something similar to this over here, where I create binary tree nodes and then I hook them all together here. I don't want to do that. Instead, I want to go ahead and jump right into it, and let's go ahead and do this insert now. Insert a new element X here. This is the binary tree. I'm going to steal that though and move it over here to my binary search tree. All right. Insert this new element X. Ideas on how to do that. Let's come over here and let's rethink our search. It's going to be very, very similar to the search. First of all, if I wanted to insert 45 into this list, all right, 50, 40, 45. Oh, it's already in there. Do we want to allow duplicates? I don't. So we could have a check. Does it contain that element? And if so, then immediately throw an exception, return, do nothing, right? Nope, no operation. So if it's in there, we don't want to allow duplicates. What if it's not in there? What if I wanted to insert, I don't know, what's something that's not in there? Let's go with 44. Insert. Well, 44 is less than 50, so 50 is greater than 44. I guess I could do something like this, a brand new node over here, and then make 50 its right child. Is that going to work? Is that a binary search tree? No, because everything over here is less than 44, but it's on the right side of 44. That's not going to work. So I can't start by working at the root. All right, well, it's got to be less than 50, so I'll go down over here. All right. In fact, what I'll do is I'll say, all right, 44, and then I'll get rid of this connection right here, right? And now I'll go ahead and hook it up. Oops, hook it up over here. There we go. That works, but it seems kind of brittle. Why? What if I had inserted 40, let's go 37 instead? Right? I just have to go down one more level, and then, you know, what am I going to do then? Let's go with 37 instead.
That tends to create linked lists rather than trees.
Yeah, and not only that, but if you inserted it right here, right? You spliced it in somehow, 37, then you'll have more than two children potentially, or something like that. All right, so let's not think at the top. Let's think at the bottom. To insert something, say insert 44, you first of all always insert as a new leaf. There's no configuration problems at all then, right? If it's a leaf, you're just growing your tree, right? It's not like you're splicing in a branch somewhere. What is that called? Grafting. There we go. It's not like you're grafting onto this tree. You're just going to go ahead and create a new bud, right? A new leaf out of it, okay? So where could I insert 44? Well, it's got to be less than 50. So come down over here. It's got to be greater than 40. It's got to be less than 45. Oh, hey, guess what? There's a spot for it. Now, it is in the middle of the tree, or it's not all the way down at the bottom of the tree. It's just a new leaf at the new location here, 44. You always insert it as a new leaf. So this is exactly the same algorithm that we just developed. First of all, you have to find it. And if it doesn't exist, guess where you are? Where it needs to be, right? That new leaf. So let's see how we can take this algorithm and maybe modify it. Oops. Whatever. There we go. Whoa. I don't know what happened there. Okay. They cut and pasted it in the console. Weird. Anyway. All right, so I'm going to start at the root element. Let me go ahead and get rid of these comments here. While you are on a current node, compare the current node to X. If it matches, stop and not return true here now because it's a void function, but well, if I found a node here that matches X. Do I allow duplicates or not?
Oh, no, that case, yeah.
So do not allow duplicates. We could throw a new illegal state exception and say that dupes are not allowed. That seems kind of harsh, though.
Why not just say, yes, I added it, because they can tell you.
Okay. They're none the wiser now, right? There we go. It's a no op, right? So here's another option. No op, which is equal no operation. Right? Just return silently. Right? Another thing that we could do is reconsider this entirely. Boolean. Right? Okay, yeah, we will we'll return true here. Or we'll return false in this case because we did not change the tree. You gave me something? Nope, it's already in there. False. I didn't put it in there. Oh, yes, it's not already in there. True. I will put it in there for you. Right? I like that because it gives even more information. You can choose to ignore that information. Right? All right, there we go. Otherwise, we'll go left. Otherwise, we'll go right. Right? Until you reach the end of the tree and you return true, we're about to put it in. Right? So place the new element, which is going to be a new binary tree node. I'll call this new node, new leaf, so that, there we go, yeah, is equal to new binary tree node containing X. Right? Place the new element at this leaf, ... And then return true to indicate it was successfully inserted. All right? Help me out. Where do I insert it? Current dot left child or set left child to this new leaf, or is it current dot set the right child to this leaf? In fact, what would current be at this point?
No.
Yeah, because I've broken out of this while loop. Okay. Yeah, null dot set. So is it going to work? If I wanted to insert 44 over here, basically my traversal has already fallen off of the tree. It's null. Can I set the child of a null? No. What do you want here? Let's go back over here. I want this parent, though. Well, if I've already fallen off the tree, can I go back to the parent?
No.
Nope. So I need to keep track of two things. I need to keep track of the current node and the previous one. So when the current node ends up being null, I still have access to the previous one. Let's go ahead and do that. Doesn't cost us anything to have more variables. There we go. Previous, and I'll start it out as null. There we go. Now, when I traverse left, I'm going to update current. Before I do that, update previous to be current. Previous, current, previous, current. Right? Now, at this point, insert this new element as a leaf of the previous. Right? So not current, because I know that current is null at this point. Previous and or previous. Which one is it? So which one? Do I set it as a left child or a right child? So here is the picture again. I'm trying to insert 44. And here is the previous value. Previous. In this particular case, I need to set it as the left child. How do I know that? Just do one more, just do one more comparison, right? How did you get here to begin with? Well, you followed this path, right? So let's go ahead and have an if, else if. Right? So if x is less than the previous dot get element, then I need to insert it as a insert as left. And I will move this up here. Otherwise, current or previous dot get element is less than x, and so we need to insert as right. There we go. There. All right, in the last 5-10 minutes here, let's think of how to test this rigorously. Ideas? JUnit? Okay, yeah, definitely would want to do JUnit. Let's go ahead and map out what we would do with JUnit here. So, for int I equals 10, I is less than or equal to 100, I plus plus, insert it. T dot insert I. Oh, I wanted to go up by tens. Plus equals 10. There we go.
That's gonna be a good test.
Yeah, I don't want 100 things. I'm satisfied with just 5 or 10, right? What's wrong? Oh, I made it for strings. Duh. All right, fine, integers. And integer, they're naturally comparable, so that's gonna work just fine. There we go. Oh, what's another quick fix that I could have done? String. Don't do that. Previous is null. All right. Let's go back over here.
When you say don't do that, you mean do that, right?
Say what? What do you mean?
Integer
Oh,
dot toString.
Yeah, don't do that. Don't just convert it just for convenience, right? Okay. What went wrong? Previous was always going to be null. Why? The root is null. So remember with linked lists, what did we have to do? We had to consider corner cases. What happens when you insert into an empty linked list? You need a new head. What happens when you insert into an empty binary search tree? You need a new root.
Oh, sure. If we had an existing tree, so
It would have worked if there was an existing tree, which is what I was depicting right here, right? But we need some corner cases. Not only that, but I'm going to think back to all those troubles that we had in designing our linked list, and I'm going to immediately say, well, wait a second. I want to keep track of the size. Private int size. This dot size is equal to 0. That way down here, what I could do is I could check that size. If this dot size is 0, there's my corner case. This dot root is equal to new binary search tree, binary tree node containing x. Return immediately. But of course, what else do you do? This dot size plus plus, right? And then return true. Don't forget, now that you're keeping track of the size, what do I do? Do I increment it here when I had no effect?
no.
Nope, dupes are not allowed. Oops. So we'll keep that.
Put it on by 3.
Yep, do it down here. It's right here. Yep. This dot size plus plus. All right. Let's try that again. Darn it. Cannot invoke comparator.compare because this .cmp is null. Oops, did I screw up somehow? Oh, I did. That was not an intentional mistake, sorry. This .cmp is equal to cmp. Oopsies. Now let's run it. It worked? Yeah. Okay. How do I know it worked?
Silence.
Yeah, silence is going. That's the Unix philosophy, right? Silence means everything worked. Right? Well, let's go ahead and test some things out, right? If, let's go ahead and do the same for loop here, right? For system.out.println t.contains. What would you expect here if it worked? True, 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 true. 10 trues, right? Hey, that works. We should test some negative things, right? Does it contain 42? False. Okay, well, I'm starting to be convinced that it works here, right? That's enough. Ship it.
Yeah.
Oh, yeah? Well, one point about testing is, can the 100 test cases, is that enough? 1,000 test cases, is that enough? I mean, it's maybe it depends, right? If you do 1,000 test cases that basically also is test the same thing, no, right? It doesn't matter how many you do if you're not testing every single possibility. In truth, I mean, testing only gives you a high probability or high confidence that it works. Unless you have a mathematical proof, and this is an area called formal verification. If you've ever heard of that before, software engineering kind of thing, theoretical software engineering kind of thing, where you actually prove this algorithm works, and here's my proof for it, and proof by induction or something like that. That's still not enough because yes, that algorithm is correct. How do you know that your translation to this particular code base was correct? And then formal verifications, formal methods are supposed to do that. There are languages that support that kind of stuff, but ultimately at the end of the day, unit testing can only provide you 99% assurance that it's correct.
Besides, the end user will break it somehow anyways.
Exactly, and that's called fuzzing, where you try to break stuff, right? You try to just throw garbage at it and see what happens. Or Netflix called it chaos testing. What would happen if this server over here suddenly went down? It would be chaos, right? Well, is our backup server over there going to work? Right, that's just a fancier, more high-level term for fuzzing. You try to screw things up to see how resilient it is. I don't know, ideas on how we could do this? I could print it out somehow, right? Do you think I drew that?
Oh, no.
No. I wrote a program that produced LaTeX code from these trees that then I just compiled and I visualized. Right? How did I do that? Well, I basically did something like this over here, right? Except that I automated it. Some other things that we could do without going that far would be, let's not just test, 10, 20, 30, 40, 50, because ultimately what's that going to look like? It's going to look like a linked list, 10, 20, 30, 40, that degenerate list that I just gave you. Let's go ahead and try to fuzz it a little bit with some randomness.
Run that same code twice.
Oh, you could do that. Oh, good. And system.out.println t.insert. There we go. So what would you expect let's go ahead and get rid of this for now. What would you expect out of this? Now that I'm printing everything. The first time that I insert everything, it should be true, 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 true. Right? The second time I try to insert everything, it should be false, 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 false. I like that test. And I have no idea if it works because I'm not actually counting these things. That's where a JUnit comes in. But here's another way that you could do it. New random. Try to fuzz it a little bit. Right? And so instead of inserting I here, let's go ahead and insert r dot next int. Get rid of this.
Going to be an integer?
Say what?
Is random going to be an integer?
I'm asking it for integers.
Oh, next integer.
Yeah, I could r dot. You can get whatever randomness you want. Next double, or next boolean, next byte. It seeds it by the current system time, so it will be different every single time. True, 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 true. If I had gotten one false there, I would have like, whoa, 2 random numbers that are exactly the same in a row. That's or in a run of 10. Nope, that ain't happening. Right? That's lotto. There's less of a chance of that than winning the lottery. Right? So true, 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 true. It looks like it works to me. What would I do now to make sure that this works? I would store these off into a separate list. List of integer, right? Values is equal to new array list. Array list. There we go. And instead of just inserting it, I will go ahead and save it off. Int x is equal to this, and then values dot add x, and then insert x at the same time, so that I could do something like this. For each one of those values, integer x in values, I need to make sure that it contains x. So once again, I will expect this to be true, 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 and then true, 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 all the way down here. I would expect 20 trues out of this thing, well, if it compiled. There we go. That looks like 20 to me. All right. Yeah, there's going to be a better way of doing this. Right? Printing it out. And so how would you print this out?
Do you have the get value, or, well, I know you pass one in too, right?
I have in order, post order, pre-order, breadth first search, right? So which one do you want? Let's look at this tree. Let's repeat our pre-order, in-order, post-order traversals here. Pre-order, what's it going to end up being? 50, then 40, then 20, then 10, then 2. Oh, it looks kind of like it's sorted. But then it would come back to 15, then 12, dot, dot, dot. Okay, that's pre. What about post-order? What would that look like?
60, 90, 95, 8.
Yeah, 60, oh, is it 60?
Oh, 50, 60, no.
I need to do left first, left, 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 left. So it would actually start with 2, right?
What? Oh,
2, and then 12. This is post order.
oh,
2, 12, 15, 10, right? Just looking at this small tree right here.
I did right side first, not left.
Oh, okay, yeah. Just flip it around.
Yeah,
We
yeah.
read left to right, unless you know another language that goes right to left. Anyway, so that doesn't look too helpful either, because it's jumping all over the place. Breadth first search, what would that look like, BFS? 50, then 40, then 60, then 20, then 45, then 90. That doesn't seem appropriate either. So I left a column here. Yeah. Tell me what in order looks like. Down here. Left, then this, then right. But before I do 15, I would do 12. So what's that going to look like? 2, 10, 12, 15. Right. Then I would come back up here and do 20, and then I would do the right sublist. 20. In the order there, I would do 24's left child that it doesn't exist. So 24, 28. Do you start seeing a pattern here? I wonder why we call it in order. Because it's in order, right? If you put stuff into a binary search tree and you do an in-order traversal, guess what you've got? A sorted list. Right? So let me show you that to you. I will simply just steal the code over here for the in-order traversal. Where is it? In order. It's going to probably work just the same. I don't think I even have to make any changes for this. Right, there we go. And let's do over here in the demo, instead of asking, does it contain, does it contain, does it contain, I will simply just have a t dot in order traversal. There we go. And what would I expect out of this? It's going to be random every single time, but every single time it should be, oops.
It's still dot.
Oh, sorry, that contains dot. Oh no, sorry, x. I just want x. Because in order is giving me a list of integers. There we go. All right, I'm going to go ahead and change this so that it's at most 100, so that I can actually read it. Right, there we go. There we go. 2, 4, 11, 25, dot, dot, dot. Run it again. Completely more random numbers. 9, 16, 18, all the way to 89. So do you see how a binary search tree is super, super useful already, even without the restriction of depth? We get sorting for free. not for free.
How do these algorithms compare, like, performance-wise? Like,
This is not great because we do not have a guarantee on the depth,
Yep.
right? So ultimately what you'd end up doing is, well, what if I gave the list to you in order? 10, 20, 30, 40, 50, now it's just a linked list. Sorting a linked list, yeah, it's in order, but there's no guarantee on that, right? All the other operations of search, delete, we haven't talked about yet, insert, now they're all order n, and you're back to square one. Right? If, as the last thing today, as a teaser for next week, I will show you how you can rebalance the tree. What if it does look like that? We're not going to get into this. This is called AVL trees or 2-3 trees, or there are dozens of balanced binary search trees. But what happens when a tree gets too skewed to the right? What you end up doing is you end up saying, okay, well, put it on a hill, right? And then take it and pull it across the hill. And what do you end up with? 20 at the top, 10, and 30. Is it still a binary search tree? Yes. Is it now balanced? Yes. All right, that's called a rotation. That's a left rotation. What do you think happens if it's skewed to the right?
right.
Or it's a left rotation, then you do a right rotation. If it's skewed back and forth, you do a combination. You rotate, and then you rotate again. Right. Now, there are a whole bunch of, it's not that simple, but that's the idea. You can get a balanced binary search tree, guaranteeing that that depth is logarithmic, guaranteeing that search, insertion, and deletion are all now order log n. Wonderful. But again, we're not going to go that far.
Like,
So, say what?
Would it be possible to convert a linked list into a binary tree?
Nope, because a linked list node only has next or previous. Now you can do what's called a trinary tree, in which case you've got a parent and then you've got 3 children, right? Or you can do a quaternary tree and you've got 4 children. Right? Why do we only stick with 2 children though?
like ones and zeros.
Ones and zeros, yeah,
Left
but
or right.
log base 2 versus log base 3. Is there a difference? Who cares? Right? You're just making it more complicated without any, any gain asymptotically. Right. All right, we'll continue there next week then.